Sarah Jabbour is a Ph.D. student in computer science and engineering department at the University of Michigan, where she is advised by professors Jenna Weens and David Foy. Her primary research interests lie at the intersection of machine learning, human-AI interaction, and healthcare, with a particular focus on the development of AI models for aiding clinicians in diagnosis and treatment decisions. So I can see she is talking about AI for clinical diagnostic decision making. Can explainability be a backstop against biased AI? So it seems to be a very wonderful talk, Sarah, and the stage is yours.
Great, thank you. I'm going to go ahead and share my screen. Okay. All right. So first, thank you for the introduction. Like Vibhuti said, I am a PhD candidate in computer science and engineering at the University of Michigan. And today I'm going to be sharing some of the research I've done throughout my PhD, specifically on building AI tools for helping clinicians make diagnostic decisions. But to start, I'm actually not going to talk about healthcare. I'm going to talk about what's on everyone's minds today, which is, of course, ChatGPT. So back when ChatGPT released a couple years ago, everyone was like, taken by storm. Like everybody was so excited about AI, and like it was available to everyone. And Margaret Mitchell, who is the chief ethics officer at Hugging Face, decided, okay, like let me test ChatGPT and see how it does. And so she prompted ChatGPT with this prompt, and she said, in this sentence, the professor told the graduate student she wasn't working hard enough. Who wasn't working hard enough? And ChatGPT's response to this was, in this sentence, she refers to the graduate student. So therefore, the graduate student is the one who the professor believed wasn't working hard enough. Okay, reasonable. ChatGPT is good at answering questions. And then Margaret re-prompted ChatGPT, and she said, in this sentence, the professor told the graduate student he wasn't working hard enough. Who wasn't working hard enough? And then ChatGPT's response to this was, in this sentence, he refers to the professor. Therefore, the sentence implies that the professor was not working hard enough according to his own assessment or the perception of the graduate student. So what happened here? Well, by switching the pronoun here, ChatGPT basically didn't allow the pronoun she to be correlated with the word professor. So women, to ChatGPT couldn't be professors. And so ChatGPT kind of ties itself into a knot to avoid having professors be women. So it's not the best look for ChatGPT, but this example reflects a very canonical example of AI bias. So unfortunately, AI is biased. And this isn't only limited to ChatGPT. So healthcare isn't immune to biases either. For example, we know that women are generally underdiagnosed for heart disease compared to men. And when pulse oximetry measurements are taken in the hospital, they're more inaccurate for darker skin patients compared to lighter skin patients. So these biases, what happens is they just end up existing in the training data that we use to train our AI models on for healthcare. And in turn, AI models could rely on these biases and reproduce or even exacerbate them when put into clinical care, and then kind of guide humans to making even more biased decisions. So what I'm going to talk about today is mitigating bias in our work, and in general has required both computational and human-in-the-loop approaches. So basically, there's no one-size-fits-all solution to this problem. Okay, so in our work, we have focused on developing AI tools for diagnosing the cause of patients' respiratory failure. And respiratory failure, or acute respiratory failure, is basically when a patient enters the hospital, they have shortness of breath, and they require mechanical ventilation. So a doctor gives them mechanical ventilation and then has to decide what is causing the patient's underlying or what's the underlying diagnosis causing this patient's respiratory failure, and then what treatment should I give based on that diagnosis. And it turns out this is actually a very difficult problem, but also an opportunity for us to build AI tools to try and help clinicians make this diagnosis. Typically, this diagnosis is based on the patient's chest X-ray, as well as varying clinical data during patient hospitalization. So this might be their laboratory results, their vital signs, their demographics. And so what we did was we sought out to build an AI model that could make this diagnosis or help clinicians make this diagnosis. So this AI model took in the patient's clinical data and their chest X-ray. We trained a deep learning model. And this deep learning model output 3 predictions corresponding to 3 very common diagnoses for respiratory failure. So pneumonia, which is treated with antibiotics, heart failure is treated with diuretics, and chronic obstructive pulmonary disease, or COPD, is treated with steroids. So it made 3 independent predictions. And you'll notice that what I have here is like 3 predictions that don't add up to 1. So this, any patient could have any combination of these 3 diagnoses or none at all. So we trained the model such that it didn't restrict to just one diagnosis. And we trained this model on 1,200 patients hospitalized with acute respiratory failure at Michigan Medicine. And we used a ground truth label for these patients by retrospective chart review. So physicians went into the chart of the patient, they looked at the entirety of the patient's hospitalization, their responses to treatments, and they told us what they believe the diagnosis was for this patient. Okay, so we trained this deep learning model, and then we measured the model performance in terms of the area under the receiver operating characteristic curve. And this just tells us what is the likelihood that the model ranks a patient positive for disease higher than a patient negative for disease. So it should output a higher probability for disease for the patient who actually has disease. And we measured AUROC in terms of the 3 conditions: pneumonia, heart failure, and COPD. And then we compared to a randomly selected physician in our data set. So we said, okay, first, like, how do clinicians do at making this diagnosis? And they do somewhere between 0.75 and 0.78 AUROC. And here our upper bound is 1, and random is 0.5. So they do about average. They do midway between random and perfect AUROC. And that's great. That agrees like with the literature telling us, this is a difficult diagnosis. They're probably not going to be perfect. And our model did just as well or even better. So it did really close in terms of pneumonia and heart failure, and it did significantly better in terms of COPD. So this is really interesting, performs on par or better than clinicians, but with significantly less information. So I mentioned earlier, the clinicians who labeled these patients for us, they had access to the entirety of the patient's hospitalization, all of their imaging, any previous history of disease, any prior hospitalizations. The AI model only had access to 1 chest X-ray at the time of respiratory failure, as well as 1 data point for each of the vitals and labs. So basically only the data at the time of respiratory failure. So that's really interesting. That was very exciting because you said, oh, the AI model does really well and on par with physicians, but with significantly less information. But typically when we have an AI model that does good, we want to ask okay, well, how is it making its decisions? Why is it doing so well for making this diagnosis? And so we ask the question, okay, how is the model making decisions using the X-rays? And often when we have AI models trained on images, we use this tool called GradCam. And this tool tells us what is the model that we just trained looking at to classify this specific image. And this looks like a heat map. So we input the image into the model, and then we generate the GradCam, which is a heat map, and it just highlights the regions on the image that the model was paying attention to when making a positive diagnosis. So here I have an example of a patient with congestive heart failure. It looks like the model is looking at the areas around the heart. When we asked our clinical collaborators, does this make sense to you? They were like, yeah, we look at an enlarged heart when making a diagnosis. This seems to be aligned with our clinical intuition. But in addition, if you focus really closely on the image, you'll notice that the model slightly focuses on the presence of a pacemaker. It's very subtle in this image, but the pacemaker has this light blue tint to it. And when asked, we asked our collaborators if they thought this was okay, the answer was not necessarily. So if the pacemaker for this patient with heart failure wasn't there, the patient's diagnosis wouldn't change. They'd still have heart failure. They'd still have an enlarged heart. They'd still have fluid or edema, on the chest X-ray. So the model shouldn't be paying attention to the fact that the patient has a pacemaker. So this concept that the model is paying attention to something that, might not be relevant, we call this a shortcut. So basically, the model focuses on something that isn't necessarily clinically relevant to disease. And so this is a general problem in computer vision. I'm going to go over like a general example of how this might manifest. Let's say we want to build a system that takes in an image and tells us if a cow is in the image. So here I have an example of, all the internet images of cows. We train our deep learning system to predict cow, and it does really well. Great. And then someone else says, okay, I have an image. I'm going to pass it through the network. And we have this image of a cow as well, and the network should predict, there's a cow in this image, but instead the network fails. It says there is no cow in this image. So what happens? Well, in all of the training data that we gave the model, all cows were on a green grassy background. So rather than learning what makes a cow, the model learns green grassy background instead. So when you show it this image of a cow on a beach, the model fails. And so this is the idea of shortcuts and models paying attention to things on images that they don't necessarily or shouldn't necessarily pay attention to. And it turns out that you could actually learn a lot of things on a chest X-ray rather than clinically relevant features of disease. So we sought to ask this question, how easy is it to infer different attributes based on chest X-rays alone? And so what we did was just train models to predict different attributes from an image, and we measured the model performance in terms of the AUROC. So in addition to being able to predict whether or not a pacemaker exists in an image really well, it turns out models could learn the patient's sex from the image. They can learn the BMI of the patient or the body mass index. It could learn the patient's age from the image. And then we also tested to see if the model could predict the patient's race from the image. So in our small cohort of 1,200 patients, we had a little bit of signal. It was above 0.5 AUROC, but not perfect. But in some follow-up work, others showed that you could actually predict the race of the patient very easily if you just have enough data. So they trained on over 200,000 chest X-rays, and the model did really well in predicting the patient race from this grayscale image. Okay, so you can learn all these different attributes, but just because you can learn something from a chest X-ray doesn't necessarily mean it's a shortcut. So what makes an attribute a shortcut? In our work, we define a shortcut as one, a spurious correlation in an AI model's training data. So for example, in the example I showed before, there might be a correlation between the presence of a pacemaker and the disease of heart failure. And this attribute is easily exploited. So it's easier to learn something else compared to the clinically relevant features of disease. For example, if you have a spurious correlation between the presence of a pacemaker and heart failure in your data, and it's easier to learn that a pacemaker is on the image rather than learn what an enlarged heart is, a model is just going to focus on the presence of that pacemaker when making a prediction for heart failure. And then the model is going to end up failing in settings where the spurious correlation no longer holds. So there might be a different prevalence of pacemakers in a different hospital. Pacemakers might just visually look different depending on what pacemakers a hospital uses. Or if pacemakers ever change, this model will start to fail because they don't look like the old pacemakers that it was trained on. On the other hand, the clinically relevant features of heart failure generally don't change. So you want the model to focus on something that's going to stay consistent throughout time, that it can robustly rely on when making predictions in new settings. Okay, so these shortcuts, they're a problem. In some of our earlier work, we said, okay, let's try to come up with some computational approaches to prevent models from learning these shortcuts when making predictions. And so to mitigate this behavior, we proposed a computational approach to shortcut mitigation. And this approach was based on the idea of transfer learning. So basically what we did was, let's say we have some biased target task, like let's say we're trying to predict heart failure, and heart failure is highly correlated with pacemakers in our training data. Instead of directly learning to predict heart failure from this data, you can train on some related source tasks. So let's say you have another data set labeled for pneumonia where the spurious correlation doesn't exist. You could basically train a model to predict pneumonia on that other data set, and then transfer the learned features to the biased target task. So basically, the model looks at chest x-rays to predict pneumonia, it learns what's relevant on a chest x-ray, and it ignores pacemakers because they're not correlated with pneumonia. And then given what it's learned, it can reuse those features to predict heart failure without having access to features that look like pacemakers. Okay, so this was great. This seemed to work pretty well in our setting, but it came with limitations. So it required knowing what the bias was in advance. So we said, I said you have to train on a related source task where this correlation doesn't exist. You have to curate that source task and make sure that the correlation doesn't exist, which means you need to know that pacemaker is a bias. And it requires access to the source data set, and we know labeling data in healthcare can be expensive, so you have to spend time curating the data set. And it only worked on one bias at a time. So you could debias a model for pacemakers, but then if you want to debias it for the patient's age or the patient's sex, you have to further curate more source task data sets, and then transfer those features to your target task. So it's definitely limited in the ability to mitigate multiple shortcuts down the line. But it worked okay. The main idea here, though, is that there's no silver bullet. We need more than computational approaches to mitigating AI bias, because we might just not know all the biases beforehand, or a model might look like it's doing really well, and then we deploy it and we find that it actually performs poorly for some certain shifts in the population. So this kind of gets us into the idea of, or the world of explainable AI. So in AI, we have this black box problem. And the idea here is that because of AI's complex nature, it's difficult for humans to understand how AI models might reach their conclusions. And so the goal of explainable AI is to make, or explainable AI aims to make the reasons behind an AI model's decisions comprehensible to humans. So hopefully, a human could look at the explanation of an AI and say, there's a bias here. And oftentimes in the explainable AI community, we say, our goal is to make AI more transparent and understandable or trustworthy. These are like just different goals of the explainable AI community. The problem is it's largely debated whether explainable AI is actually useful to end users. So often explainable AI techniques are built for computer scientists, and they're not necessarily built for end users who haven't interacted with AI before in whatever task they're doing. So those that are for explainable AI have suggested that it could be a tool that helps users perform better with AI and expose problematic behavior. And this is ideally what we would want with our AI, with our ARF model. So if we develop a model that seems to do really well, we still want end users to be able to understand the model and hopefully perform better with it if provided explanations. There was a study that investigated if model explanations could help users debug errors in models. And what they tested was if a model takes a shortcut, their users told them that they saw somewhat of an unexpected explanation for the model prediction. So they seemed to notice that something was up when given the explanation for the model that took a shortcut. Others in the healthcare space have argued that with the help of interpretability methods, the next generation of radiology will likely experience full use and enhanced trust in AI and deep learning. So there are others who are very, very pro explainable AI as a way to really integrate it into healthcare. On the other hand, there are concerns in the explainable AI community that current explainability approaches could cause problems during decision-making. So for example, there was a study recently where they looked at explainability in terms of user trust, and they found that AI model explainability could increase user trust, but also showed that if an AI model is trustworthy, it could trick users into trusting it when it wasn't necessarily performing up to standards. And the idea there was that the AI model simply just told the users that it could perform well, when in reality, it actually performed poorly. So it emulated this idea of trust and it convinced the users to trust it, but in the background, the AI was actually performing poorly and they still relied on it. There was another study that showed that when choosing treatments for major depressive disorders, if you provided clinicians with an AI to help them choose these treatments better, they found that if the AI was wrong and you also provided an AI explanation, the users were more likely to rely on the AI when it was wrong. So this was causing problems in a clinical setting. So there really isn't yet a consensus on if we should be using explanations with end users, because the community seems to be split. There are some cases where it seems to work, some cases where it seems to not work. At least for now, it seems like the FDA is on the side of explainability is good. So 2 years ago, the FDA issued guidance regarding how it interprets rules around clinical decision support software in the Affordable Care Act. And specifically, what they said was it excludes certain software functions from the definition of a device and thus regulation if that device meets specific criteria, and one of these criteria relies on explanations. So the idea here is that an AI explanations should enable healthcare professionals to independently review the basis of software recommendations so that they don't rely primarily on the AI when it's wrong in making a clinical diagnosis. And thus the FDA just wouldn't regulate that device if it meets that criteria. The problem is that to date, this approach has not been tested. So we're very limited in terms of clinician-AI interaction studies, and we can't really support such policy because we don't know if these approaches work. So we sought to test this. We sought to test the questions, can explanations help? And we hypothesized that real-time local explanations, which I'll define in a couple slides, can help clinicians discern good model advice from bad model advice. So for example, if I showed clinicians this GradCam explanation of a model that focuses on features or in the lung area, this could be considered good advice. On the other hand, if I showed a GradCam explanation where the model focuses on the shoulder blades, you could consider this bad advice. And hopefully, given these two different explanations, a clinician would be able to tell which one they should rely on and which one they shouldn't. We chose GradCam specifically because this explanation method is widely used in the development of AI models based on images. So the GradCam paper has over 17,000 citations, and in the paper, they even claim that through extensive human studies, they reveal that their visualizations can help identify biases in data sets. So we said, okay, this is what everybody generally uses for debugging AI models. Let's see if end users can use them as well. And so our approach to this was a web-based clinical vignette survey study in which participants were presented with clinical vignettes of real patients hospitalized with acute respiratory failure, and we tested to see how AI models would affect their diagnostic decisions. Okay, so here's what I mean by local explanations. When we train models on images, we actually don't have any existing tools to understand the overall model behavior. We really can only understand how the model makes a decision based on each image instance alone. So you can pass this image through the model and it will tell us the model pays attention to the areas highlighted in yellow when making a diagnostic prediction for this specific patient. And then you can generate this for every single chest X-ray that you pass through the model. Yeah, so we can generate this explanation for every single patient the AI sees at deployment or at the bedside. So in terms of our study setup, we showed each clinician a series of vignettes of patients with acute respiratory failure, like the one shown here. And this included various amounts of information, like the patient history, the medical history, their social history, their chest X-ray, lab results, all the information they need to make a diagnosis. And then we asked clinicians to rate the likelihood that each of these three underlying diagnoses, pneumonia, heart failure, and COPD, was contributing to the patient's respiratory failure. And here 0 is unlikely, 100 is likely, and we told the participants this did not need to add up to 100. They could have any combination of the three diagnoses. And then finally, we asked them if they would administer any of the commonly used treatments for these three conditions to this patient as well. Okay, in terms of the patients that the model was applied to, we had a patient population of 45 patients, and overall, model performance was reasonable. So overall, we had model performance around 76% accuracy. You might think of this as if you spend the time developing an AI tool, you're not going to deploy it until you think it does reasonably well. And so we tried to emulate this. And here, for most of the patients, we had standard predictions. These were predictions that came from an AI model trained using standard approaches, and it did pretty well. And then you had a small subset of patients where the model took a shortcut and fails. And so here the model is biased for the set of patients and it generally does poor. But if you look at the overall distribution, this kind of looks like, hey, the model does pretty good. We just don't know or are unaware that the model is performing poorly in this very small subset of patients. And hopefully the clinicians will then catch that at the bedside. So in addition, so this model, what did the AI input look like? The algorithm estimated, again, how likely the patient's current symptoms were due to each of the three diagnoses. And if the participants if the model made a positive prediction, it also showed the explanation, here again, highlighting the regions the model was using to diagnose disease. To measure participants' baseline performance, all participants first completed 2 vignettes without any model assistance. Then for the next 6 vignettes, they were either randomized to see model predictions alone or model predictions with explanations. And the goal here was to compare the 2 groups. Within those 6 vignettes, they saw 3 standard model vignettes of reasonable accuracy and then 3 biased model predictions with very poor accuracy. And within those, we randomized the order of the 6 vignettes as well, so that we wouldn't anchor them to one specific model in terms of their expectation of model behavior. Okay, so what do we expect in terms of results? I want to highlight that we showed participants overtly biased explanations. We tested a very extreme setting. So here I have to compare to standard explanations. The model pays attention to reasonable areas on the image. And then we have very overtly biased explanations where the model is focusing on things that would be really crazy for a clinician to focus on. So here I have the model paying attention to the shoulder blade outside the lung. Ideally, a clinician would look at this and say, there's no way this model is right. I'm going to ignore the model when shown these biased explanations. And hopefully they'd recover to their baseline performance, which is just their performance without any AI model input. In terms of evaluation, we had a reference label where 4 or more pulmonary physicians independently reviewed each patient's complete medical record and determined if pneumonia, heart failure, or COPD was the patient's underlying diagnosis. The primary outcome for the study was participants' diagnostic accuracy, and this was considered correct if the participants' assessment agreed with the reference label. And then the secondary outcome was the participant's treatment accuracy. So this was considered correct if the participant's treatment choice agreed with what was administered to the patient during hospitalization. Okay, so in terms of results, over a 7-month period, participants were recruited from major academic hospitals across the US. We received in total 572 participant responses, 418 of which completed all 9 vignettes. Of these, 284 participants saw the AI model alone, and then 288 participants saw the AI model with corresponding explanations. And then overall, 98% of participants practiced hospital medicine. And this was really important to us. So hospitals physicians are taking care of respiratory failure patients all the time. They're the expert at this diagnosis. So they ideally should be able to make relatively good diagnoses for these patients at baseline. Okay, so in terms of results, again, the first question we asked was, how do these AI predictions affect clinicians' diagnostic accuracy? And at baseline, clinicians were about 73% accurate. This aligns with the literature that tells us that clinicians are wrong about 30% of the time for this diagnosis. Again, this is a very difficult diagnosis for clinicians to make. When given a standard model, clinicians made better diagnostic decisions. So we had about a 3% bump in clinician accuracy. And then when given the standard model plus explanations, the explanations just amplified this effect. So we got close to 78% accuracy, or a 5% increase in diagnostic accuracy overall. And this was really exciting because, like I mentioned before, our standard model was only about 76% accurate. So it wasn't perfect, but clinicians plus the standard model did better than each of them alone. And this is kind of like complementary behavior in terms of like clinician-AI collaboration. On the other hand, when given a biased model prediction alone, clinicians' diagnostic decisions were really harmed. So we had an over 10% drop in diagnostic accuracy. And then when given explanations, the explanations just didn't help clinicians recover to baseline. So these explanations that I mentioned before that were overtly biased didn't really signal much to clinicians that they should ignore the AI model, and they barely had any kind of recovery. So in addition to these results, we also ran some subgroup analyses to see if the biased explanations help any subgroups of the clinicians. We first split by provider type, so whether or not they were a nurse practitioner and physician assistant, or a physician with an MD. We found that when given systematically biased models compared to their baseline, which is the middle line here, they did significantly worse, and the explanations again didn't help them recover. And then again, with physicians who had an MD, we found the same behavior. So systematically biased models hurt, explanations didn't help them recover. We also looked at if we could subgroup by their prior interaction with AI. So did clinicians interacted with clinical decision support tools before in their practice? What we found was that if they had prior interaction, again, we had the same behavior. Biased models hurt, explanations don't help. And then if they didn't have interaction before, same behavior as well. So no matter how we split the data, we didn't really find that the explanations helped. Okay, so in addition to diagnostic accuracy, I mentioned that we also looked at physicians' treatment accuracy. And so in terms of treatment accuracy, clinicians alone, again, do about 70% accurate at choosing treatments. This aligns with the clinical literature. When given a correct model, or when the AI gets it right, clinicians make better treatment decisions. So this is really promising. And then when given a correct model with its corresponding explanations again amplify this effect. So that's great. Again, what we want to see. On the other hand, when given an incorrect model, clinicians fail to make the correct treatment choice. We have an over 15% or about 15% drop in clinicians' treatment accuracy. And then when given an incorrect model with explanations, again, explanations don't remedy this effect. So clinicians are still over-relying on the model. So that's our results in terms of diagnostic and treatment accuracy. What I didn't mention was that we actually had a 9th vignette in this study. And in this vignette, oh, I forgot to mention, sorry, similar results in subgroup analyses, which are in the paper. Okay, so we had a 9th vignette, and this 9th vignette was a clinical consult. What I mean by this is we presented a vignette where we gave them a consult from what we called a trusted colleague, which was always correct. And the idea here was to measure an upper bound on clinical or clinician performance. What happens, if we gave them a perfectly accurate model? And so this is what the note looked like. We said a trusted colleague who saw this patient wrote this in their consult note. I think, for example, I think heart failure is very likely the underlying cause of her acute respiratory failure. I would recommend aggressive diuresis. So we gave them the correct diagnostic decision as well as the correct treatment. Again, this note was always 100% accurate. So in terms of the results there, just to remind you, in terms of diagnostic accuracy, clinicians alone were about 73% accurate. And with a standard model and its corresponding explanation, clinicians were about a little under 78% accurate. And then given a clinical consult, again, that was 100% accurate. Clinicians only performed at 81% accuracy. So they still perform less than perfect for this clinical diagnosis. So this just highlights, one, we somewhat have an upper bound on how well clinicians can do if we gave them an AI model. We shouldn't necessarily be aiming for perfect clinician accuracy, but we might be bounded by this 81% because clinicians disagree on this diagnosis all the time. Okay, so we had some thoughts about why clinicians couldn't catch bias in this study. The first was that of only 23% of participants were aware that AI models could be biased. So informing clinicians of AI strengths and weaknesses might better equip them to catch when a model is wrong. It's kind of a problem of unknown unknowns. They don't really know what they're looking for necessarily, especially if they don't know that AI models could be biased. They were only shown a small number of vignettes with explanations. So I mentioned they only had up to 6 vignettes with explanations, and they might just need more training with AI explanations in order to leverage them more. And then finally, heat map explanations, like I showed here, can't communicate in plain language to clinicians what they're looking at. So I mentioned we had this explanation where it looked at the shoulder blade. In that case, the model was focused on the patient age, but it wasn't communicating that in plain language to the physicians. So explanations might be more helpful from a model if they were presented differently, like a text explanation saying, this is what the model thinks, and this is why. Okay, so in terms of next steps, what might be some paths forward to try to safely integrate AI into healthcare? One is incorporating more AI into medical training. So the majority of the participants in our study didn't have prior interaction with AI tools in their clinical decision making. And so they might just not know how to leverage AI and understand what are the strengths, what are the weaknesses of AI models, when should I be more aware that the AI model might be wrong versus right. Additionally, we were kind of calling for more diverse collaboration. So this study, we took input from AI experts as well as, physicians, radiologists, human-computer interaction experts to really try to understand the scope of how we could help the end users. But the explanation that we tested was generated or developed in more of a siloed setting where AI researchers were developing the explanations for themselves rather than the end users. So we need more diverse collaborations across these settings so that we can really understand what end users want. And then finally, just more continued model validation during development. So we shouldn't just stop at trying to mitigate one bias. We should really vet the models before we're comfortable sending them into clinical practice. And we should continue working on computational approaches to continue mitigating bias before AI even gets deployed into the clinical setting. Okay, so overall, just to recap, our study shows that model predictions can hurt clinical decisions, and current explanation approaches that are widely used just aren't a good stopgap to mitigating this. Clinicians might need more training with AI models before they're ready to use them in their clinical practice. And then we just need more approaches to understanding models and continued vigilance in terms of catching biases before a model is deployed. And then big thanks to my collaborators. I had a really nice team that were very diverse, lots of backgrounds to run this study. And it was super helpful to get their input.
Thank you very much, Sarah. It was a really interesting talk. I really enjoyed it and learned a lot of things from your research. So you are basically combining the explainability and the fairness part in your research. So that's really interesting.
Thank you.
I have a couple of questions, and then we will go with with our audience.
Mhm.
So you said that in your first paper where you are working on the acute respiratory failure condition detection from the X-ray images,
Mhm.
you said that you have compared the ROC values with the physicians.
Mhm.
So how does physician determine those ROC values, or how did you measure that when
Mhm.
you compare your results?
Yeah, that's a good question. So what we did was for every single patient, we had 3 or more physicians who made a diagnosis for this patient. So what we did was we randomly selected for each patient one of those physicians to act as the prediction, and then we used the average of the other 2 physicians to be the ground truth. And then we had basically a list of predictions and ground truth values for each of the patients, and then we could calculate the AUROC.
Okay, okay, sounds good. Another question is, like you said that when we uh, when we go with the cons of the explainability, and there is some work in the literature in which uh, the outcomes are worse when we basically try to be more explainable. So
Mhm.
what are your thoughts on that part? Like you demonstrated your work in that, but I was actually that is really interesting and new for me to
Mhm.
understand. Yeah.
Yeah. Yeah, so the issue right now is that the literature is definitely split, in that some have shown that if you have an incorrect AI model and then you give them an explanation, they might rely on it more. Um, the explanations tested in that study were feature-based explanations. So it was like, here's all the features that are input to the model, like tabular data features, and then here is the feature importance. We tested a different type of explanation where, when the bias model was wrong, clinicians were hurt, but then the explanation didn't actually make them worse. So there was a little bit of different behavior, and I think it's because one type of explanation might cause more automation bias compared to another type of explanation.
Mm.
And in our setting, it just so happened that it didn't cause more automation bias. So I think it's very nuanced in terms of like, what is the setting? And then, clinician, there's so many like confounding factors. What is the clinician's background? What is the decision that they're trying to make? What type of explanation are you using? So I think, yeah, overall, consistently, much of the literature has shown that when AI is wrong, there is automation bias and we need to mitigate it.
Mm.
But there are definitely different behaviors depending on the setting and the explanation and the end task, that where the interaction with explanations looks slightly different.
Okay, great. Yeah, thank you. We have a question from audience.
Mhm.
This is from Dr. Kao. What is your gold standard when evaluate physician performance?
Mhm. Yeah, so here we had the reference label, where for more pulmonary physicians looked at the entirety of the patient chart and told us what the patient's diagnosis was, given like the patient's condition as well as their response to treatment.
Okay, okay. Um, is there any other questions from the audience? You can unmute yourself and ask or put it on the chat. Yeah. Yes, Dr. Kao.
Yes, this is a very interesting talk. Is the message also very interesting message I learned from this talk. So it looks like the bears from the model, the AI model, that it can help the physician, but it can also not help the physician, right? So yeah, it's the message is very interesting. So I learned this.
Great, thank you.
It's not exact, yeah, and I don't think it's exactly a question, but it's just like when you demonstrate at the end, say if it is a good model, then it helps the physician to increase their performance. But if the model is not good, then it actually hurts the physician.
Mhm.
So it's really a question that if there is a model, should we trust it or not? So this is a really good topic.
Yeah, for sure. And I think so there's still a lot of work to be done on how do you decide when a model is ready to be deployed. Like many models could look like they're doing well, some of which might be biased, in some very small subpopulation. And I think we need to figure out, what is that threshold? What's a reasonable sensitivity and specificity? Just like laboratory tests aren't perfect either, but we have some level of sensitivity and specificity that physicians are willing, to take in terms of deploying the lab test. I think it can be thought of in the same way. And then we also need processes in place for where if the AI model is wrong, it doesn't necessarily mean that the physician is necessarily liable. So we know, I think we can take a lot of inspiration from the airline industry where, when autopilot became a thing, they kind of they have these processes in place where if something goes wrong, the pilot can report it and then the pilot isn't liable. Like they want a an atmosphere where you should feel comfortable reporting that something is wrong. So I think there's a lot of questions around like, at what point do we decide to deploy? What is reasonable? What are the consequences when it's wrong? And those are still a lot of unanswered questions.
Yeah.
Exactly.
Yeah. Go ahead.
Right. So can I ask you one more question? So you have your sample size about 500, over 500. Among these 500 patients, what's number of the disease patient? Like, how many patient has COPD? How many has different, the outcome that they are interested? Is that small portion or, relatively is good number?
I think it was around, I'd have to check the paper to make sure, but I think it was around 20% had COPD, and then
Gotcha.
40-ish% had pneumonia and heart failure. So that the 40% matched with our overall clinical population that we had when we like subsetted into the subset of patients. And then for COPD, we upsampled a little bit because COPD actually is significantly lower prevalence compared to pneumonia and heart failure.
Gotcha. Thank you so much. It's really good work.
Great, thank you.
Yeah. Sarah, I just missed another question I just got through when I was going through your presentation. So when you were presenting about inferring attributes based on the X-ray images, like these demographic factors, so like how did you basically predict the age and sex based on just the image as input?
Correct. Yes. So we train the models to directly predict them to see how well could the model do. Like if the model couldn't predict it, then we knew it just can't learn those features from the X-ray or that attribute. But it turns out it can learn a lot of things from the X-ray if you just train it to predict it.
Okay, and did you find that in the outcomes, is there any kind of a bias exist, like in terms of a gender bias or other types of biases?
Yeah, so we had so pneumonia is generally correlated with age. So there is a correlation there. And I guess to clarify one thing, it's not necessarily a problem if that correlation holds across populations. It's
Okay.
only a problem when that correlation breaks. So pneumonia we know is generally correlated with age. We know heart disease is generally correlated with patient sex. And early on in the development of the model, we also noticed that pneumonia was correlated with the text in the corner of the image. So sometimes the model would focus on the text in the corner of the chest X-ray rather than on the lungs. And that's kind of what spurred the discussion of like, why isn't the model focusing on what the model should focus on?
Okay. And in all your experiments, have you thought of comparing that with the ChatGPT or the MedPalm tools, like for the
Yeah.
kind of like comparing your performance with them? I was just
Yeah.
wondering, like,
Yeah, that's a good question. I'm waiting, unfortunately, because it's Michigan medicine data. I can't input anything into
yeah,
ChatGPT.
that's true.
So I'm waiting for the time when we can actually test to see like how well do these models do. But for now, unfortunately, I can't.
That's true.
Restricted in what I can put into ChatGPT.
Yeah, you cannot directly put that because it's an EHR data, right? Yeah. Okay. So we have another question from the student, just a couple of minutes more. So what did you enjoy the most working on this project?
Yeah, so in general, I like at baseline, I really enjoy my work because I want to work on something where I feel like I can help people in the end. And so that's why I decided to do AI for healthcare. I think in the human computer interaction study, it was definitely a learning experience. So coming from like a purely AI working in the lab background to actually understanding how humans interact with AI was very eye-opening because I realized like we've kind of figured out how to train AI models. We really haven't figured out how to use them. And all of this work that we do in terms of making better models that can make better predictions is going to be useless unless we can actually get humans to leverage them. And so understanding like all of the different aspects, how does the human interact with the AI? What does the policy say? Who becomes liable? It kind of started to bring up all these questions and really makes you think like, I need to make sure that the tool I'm building can be used correctly and safely And then what are all the different repercussions when that doesn't happen? So it was definitely a learning experience and kind of opened my eyes to, we really have to start thinking about the end users if we actually want to get AI models into clinical care.
Okay. Yeah. Thank you, Sarah. I think overall it's a really wonderful presentation. Great to know about your research, and we will
Great, thank you.
definitely. I think I haven't met with Dr. Weens from a long time. Might be we will talk later and have think about some of the collaborative opportunities for sure.
Yes, absolutely.